Hello guys, this is Avinash and you're watching Everything Metallurgy. So in this series of ferrous extraction, we are dealing with the steel making now. We have already did two videos under steel making. So this is the third video of steel making in which we'll be discussing about all the oxidation reactions. Okay, so first of all, you must know in steel making there are many impurities. There are many impurities present. So what are these impurities? The impurities may be carbon, silicon, manganese, phosphorus and sulfur. So generally these are the impurity atoms that are present in the steel or the hot metal. Okay. So these must be removed either by the gas metal reactions or the gas slag reactions or the metal slag reactions. That means between the interface of all these what I have just said, there will be reactions taking place in order to remove all these impurities. Okay, so to produce desired chemistry, of steel, we need to remove these and we need to control the weight percentages of these. So generally, the composition of all these impurities are expressed in the terms of weight percentage. Okay, expressed in the terms of weight percentage or sometimes mole fraction also. So we know what is weight percentage and what is mole fraction. Mole fraction is nothing but the number of moles of some component I to the total number of moles in the system. The total number of moles of components present in a system. So that is equal to the mole fraction. Okay, so these are some general formula which we'll be discussing now. So what is the formula for Gibbs free energy? So the formula for Gibbs free energy is delta G equal to minus RT ln K. Okay, if we know the equilibrium constant of any reaction that we have that will be taking place in the steel making, this is the Gibbs free energy formula, K, where K is the equilibrium constant. So similarly, if we know the activity, then the same formula will be RT ln A. So all this stuff will be discussed in thermodynamics. Okay, but these are also important in steel making, so I'm just revising it briefly. So what is this A? A is the activity and K is the equilibrium constant. So what is this A? Activity is nothing but the ratio of fugacities. Activity of a component denotes its effective concentration with respect to the concentration of its pure state. That is known as activity. Okay. And one more thing that is very important in steel making is the chemical potential. Chemical potential. So this chemical potential is very important because an impurity can transfer in slag phase or some gas phase only if its chemical potential is less than that of the chemical potential in the hot metal. That means the impurities present in the hot metal are removed into the slag or some gases only if its activity or chemical potential is less than that of its chemical potential present in the hot metal. Okay, that is why the chemical potential is very important. So these are about the basic formulae that are required here, and also you must know about the Raoult's law and the Henry's law. Okay, so I think all this you will be studying in the thermodynamics. So Raoult's law is nothing but the activity is proportional to the mole fraction where A will be equal to gamma x. Okay, so for according to Raoult's law, an ideal solution has an activity equal to its mole fraction, but this formula is used for a deviation where if the solution is undergoing some deviation from the Raoult's law, then this is the formula where gamma is the activity coefficient. Okay, so this is about the Raoult's law. Similarly, Henry's law. Henry's law also has the same thing, but here this HI is known as Henryan activity coefficient. That means, what is the difference between these both? The difference is that the Henry's law is used only for dilute solutions. It is used only for dilute solutions. Dilute solutions in the sense the presence of solute is very less. Here, the liquid steel or the hot metal are all dilute solutions because the minor constituents are present. The other impurities are very minor in composition. Okay, so you can calculate the activity from this Henryan coefficient by using this formula. Hi equal to Fi into the weight percentage of that particular component. Okay, so activity or Henryan activity coefficient equal to the fugacity of it into the weight percentages. So using this, there is a formula for Fi using the concept of interaction parameter. Using the concept of interaction parameter, the formula for log Fi is equal to E11 into weight percentage of 1 plus E12 into weight percentage of 2. Here we are calculating for F1 and so on. That means log Fi is equal to sigma Ei to n, where n will be equal to 1 to I. Okay, and similarly I will be the constant. This is the formula where Eij is known as the interaction parameter between the components I and J. Okay, so you'll get to know if you solve any questions in the previous year. So this is nothing but this interaction parameter describes the influence of solute J on the activity coefficient of solute I. So there will be some interaction between these two. This interaction parameter determines the influence of one solute on the other solute. Okay, so remember this formula. So it will be useful in solving some questions. So now we'll see the principal reactions that will be taking place in the steel making. What are the important reactions that are taking place in steel making? So as I already discussed previously, iron making is a reduction process, whereas the steel making is an oxidation process. Yes, why? Because we can easily say that we are sending oxygen from the lands. We are sending oxygen from the lands at a very high pressure, so that obviously the oxygen from the lands react with the components of the hot metal. So these are the different reactions or different oxidation reactions that take place. And here you must observe that all the products, all the products that are formed are forming slag except this reaction. That means this carbon monoxide is produced. That means the carbon is removed in the form of gaseous phase. Only carbon is removed in the gaseous phase and the rest all will go into the slag phase. What is a slag? Slag is again a separate layer that is formed which consists of these different oxides and sulfides. Okay, so always remember all these reactions are exothermic in nature. That is the reason why we are not providing any heat. These exothermic reactions are producing the heat which are sufficient enough for the reaction to take place. Okay, so this is about the principal reactions, the different reactions that will be taking place in steel making. And here you must observe one more thing, that even iron from the hot metal is getting oxidized. That means iron oxidation is unavoidable. Okay, it produces some loss. The iron, it is known as iron loss, and it must be controlled. Okay, and one more thing you need to observe is all these are the oxygen that is reacting with different components is the dissolved oxygen in the hot metal. So for all this reaction to take place, the oxygen must be dissolved in the hot metal to remove the any impurities present in the hot metal. Okay, so these are the principal reactions in steel making. So now we'll see individually, we'll be looking at each oxidation reaction. Okay, the first and important one is the iron oxidation. Iron oxidation. So oxidation of iron is very important because it controls the FeO content of the slag. If it is oxidizing, if Fe is oxidizing, it forms FeO and it controls the FeO content in the slag. And why this is important? Because we have discussed about the oxidizing and reducing potential of the slag. The FeO content determines whether the slag oxidizes or reduces. Okay, so it is important to know or to control the FeO content in the slag. Okay, and what else? It also controls the loss of iron into the slag phase. So forming this FeO is not only useful for reducing or oxidizing, but it is also producing some loss in iron into the when it is going into the slag, and it affects the productivity. Okay, and obviously we know from this point only, it also controls the oxidation or oxidizing potential of the slag. Okay, so these are the important features or the features of the iron oxidation. So the oxidation of iron is most important, so that these may be affected because of iron oxidation. So the next important thing that we'll going to discuss is the silicon oxidation. So what is the silicon oxidation? That is Si plus 2O gives rise to SiO2. Okay, the silicon from the hot metal is reacting with the oxygen and forming SiO2, which go into the slag phase. So what are the favorable conditions for this? Okay, so we'll be discussing about the favorable conditions for all the oxidations. So here, if you observe here, this the number of moles, or okay, one more thing you have to know is this is an exothermic reaction. All the reactions that are taking place is an exothermic reaction. So according to Le Chatelier principle, for the forward reaction, that means in this case for the oxidation of silicon, it require low temperature. Okay, low temperature is favorable for all the exothermic reactions in the forward direction. And similarly, low activity in the slag, low activity of SiO2 in the slag. Okay, and why we'll be discussing now. See, if the weight or the activity of product is decreased, the forward reaction will be taking place. If there is a reaction A plus B gives rise to C, if we are removing C continuously, the formation of C will be faster. So in the same way, if we have low activity in the slag acts as a sink for SiO2, and further SiO2 formation will be taking place. So low temperature and low activity of SiO2 in the slag are the favorable conditions for silicon oxidation. So how to get this low activity of SiO2? Low activity of SiO2 is present in the basic slag. That means in the slag which has basicity greater than 1, the acidic oxide content is less. So the activity of SiO2, because SiO2 is acidic acid, acidic oxide, so it is also low. So the basic slag favors silicon removal or silicon oxidation. Fine. So these are the favorable conditions for the silicon oxidation. So as I already said, in a basic slag, the silicon oxidation occurs to very low value because the SiO2 reacts with CaO again. Okay, we know that if CaO is present in a basic slag, CaO is present in more extent. So this will be reacting and the hexagonal network is broken and decreases the activity of the SiO2 to further lower values. Okay, so this is again another important feature of a basic slag in the silicon oxidation. So, and one more thing you have to remember is silicon has very high affinity with oxygen, so it can easily be oxidized. So silicon is generally used as a deoxidizing agent in the form of FeSi because silicon can easily react with oxygen. FeSi is added as a deoxidizing agent so that the oxygen can be removed out. Okay, so this is the silicon oxidation that will be taking place in the steel making. Okay, now we'll move on to the manganese, the oxidation of manganese. Okay, oxidation of manganese. So what is this? Oxidation of manganese is Mn plus O gives rise to MnO, and the Mn reacts with the slag at the slag metal interface, means FeO of the slag, and it forms MnO plus Fe. That means the iron recovery is taking place in this particular reaction, and this takes place at the slag metal interface, and this takes place using the dissolved oxygen. Okay, so what are the favorable conditions? Again, these are exothermic in nature, so low temperature is favorable. Low temperature is favorable. Okay, this is for removal of Mn. These conditions are for removal or oxidation of Mn. Okay, so as it is an exothermic reaction, it is low temperature is favorable. Now, if you see this reaction, what happens if the activity of FeO increases? If the reactant is increasing, the forward reaction will be more enough and good enough. So the FeO content in the slag must be high enough. That is, it is an oxidizing slag. We know why it is an oxidizing. So if you are confused with this, please watch the slag in the steel making video, the last video, in which I have explained about how the FeO content in the slag controls the oxidizing and reducing potential of a slag. Fine. So FeO in the slag will be increased. If the FeO content in the slag increases, that is, for an oxidizing slag, the forward reaction will be taking place. So this is the condition for oxidation of Mn. So now, what may be the condition of reduction of MnO? What may be the condition for reduction of MnO? The same opposite thing. That means the reverse reaction of this. If we want to recover this MnO from the slag, the conditions will be, because we have reversed, it will be high temperature and this is a reduction reaction, and if we increase this, what happens? The backward reaction takes place. So we have to decrease here such that the forward reaction will be taking place. So here, for the reduction of MnO in the slag, the conditions are high temperature and reducing slag. Okay, reducing slag or low FeO activity. Fine. So this is about the oxidation of Mn, and why we are considering about the reverse reaction, that is the reduction of MnO, is it transfers this Mn into the hot metal. It transfers the Mn from the slag to the hot metal and increases the concentration of Mn. and increases the concentration of Mn, and the concentration of Mn is beneficial in the steel because it reduces or compensates the hot shortness that is provided or produced due to the sulfur. This we have already discussed in the effect of impurity atoms. Fine. So this is about oxidation of manganese. So now we'll discuss about the oxidation of carbon. So in this video we'll discuss about carbon, and I'll make a separate video for desulfurization and dephosphorylation. Okay, so in this video we'll study about decarburizing. So what is this decarburizing? So decarburizing is nothing but the oxidation of carbon or the removal of carbon. C plus O gives rise to CO. Okay, this is the reaction, and this is the only reaction where the reactant is removed in the form of a gaseous phase. Okay, this is the only reaction where the carbon or any element in the iron is removed in the gaseous form. Okay, so what is the significance of this reaction? What we'll see the significance. Okay, what is the significance of this reaction? The main thing is, as it is a gas, the CO gas during its escape, obviously it will be escaping out of the furnace. So during its escape from the molten bath, it can induce stirring. Okay, it can induce stirring in the metal and also as well as slag. So because of this, the homogenization of the steel will be taking place. Okay, so also because of CO, slag forming take place. We have discussed what is slag forming. If the CO is not able to escape out, the foaming takes place and the slag thickness or foam thickness increases, which leads to increase in the reaction surface area, which is again a good thing. So slag forming is feasible unless the slag is not overflowing from the reactor. So the CO is induced the stirring and also slag forming takes place, and also this CO has very high calorific value. It has a very high calorific value, and this combustion, the combustion of CO produces high energies. Okay, so we'll be discussing about this in the post combustion. So this CO is again combusted so that the energy efficiency is developed, so the energy can be efficiently again used. Fine, so these are the significance of this gaseous CO that is formed during the oxidation of carbon or the removal of carbon. So now similarly we'll see what may be the effects. So decrease in the carbon content increases the oxygen content of the steel. Okay, why we'll be discussing now. Decrease in the carbon content increases the oxygen, or you can call the dissolved oxygen. Okay, so this is very important in the production of ultra low carbon steels, because precautions must be taken as the carbon is decreasing and decreasing. It is not reacting with any oxygen, and this extra oxygen is dissolved into the hot metal. So this will be accompanied with the dissolved oxygen, and increase in the partial pressure of CO increases the weight percentage of oxygen in the steel. Okay, so always remember, increase in the partial pressure of CO, that is PCO, also increases the weight percentage of O2. Why? Because see, this is the reaction in which we are talking about this. The first thing, decrease in the carbon. If this is decreasing, what happens? The backward reaction takes place and the oxygen content will increases the percentage of dissolved oxygen. In the same way here, if we increase the product pressure, as it is a gas, if we increase it, again the backward reaction takes place and oxygen will be dissolved in the hot metal and it increases the weight percent of O2. So that is what we have discussed till now. Fine. So now what is a rimming reaction? Rimming reaction is nothing but the evolution of CO. Rimming is nothing but the partial oxidation of a steel. Okay. So rimming reaction is nothing but the evolution of CO during the solidification. If there is some oxygen left out in the hot metal, then what happens? It reacts with the carbon and CO is this evolution of CO takes place during the solidification, and also here also it induces stirring. Okay, in stirring in the solidification of liquid steel, and due to this it minimizes the segregation of the solutes. Okay, as it is stirring, the solutes are uniformly distributed. So this is the advantage of CO, or you can call the partial partial oxidation. That means some oxygen is left out in the steel, which is again reacting with the carbon, and this CO is evaluated. Okay, so this is about decarburizing or the carbon oxidation. So thank you guys. This is a video in which we have discussed about only 3 or 4 oxidations, that is iron, silicon, manganese and carbon. So dephosphorylation and desulfurization are very important. So I'll be discussing these both in a single video in the coming lecture. So thank you guys. Give this video a like and please share with all GATE aspirants and let them know about everything metallurgy. So thank you guys.